Alright, this is section 10.5 where we're going to delve a little deeper into something called gas stoichiometry. So let's just review really quick a little bit of the steps of stoichiometry, and you'll see where the new gas law equations fit in. First of all, you always have to have a balanced chemical equation. And in our sample problem here, you can already see a balanced chemical equation right up here that we're going to use. Second, you have to convert to moles. We now have a new way to convert to moles. We have PV equals nRT. Solve for moles. PV divided by RT is equal to moles. Sometimes you use that. Sometimes you use the periodic table. Third, we use the multimole ratio, which is the heart of stoichiometry, and that you need the coefficients in front of the balanced chemical equation pieces. And then lastly, you have to convert to the asked for units. And now, lots of times, we'll be asked to find the volume. And of course, we have a new way to find the volume of a gas, where V equals to nRT divided by P. So pervnert becomes really important in the steps to stoichiometry because 2 of the 4 steps involve units. That might be moles, might be volume, could be pressure even, but they become a portion of what we're doing. So lots of times the volume is known at standard temperature and pressure, or you want to know the volume at standard temperature and pressure. And standard temperature and pressure is many times abbreviated STP, standing for standard temperature and pressure. So standard temperature and pressure is 273 Kelvin, 0 degrees Celsius, 273 Kelvin, and standard pressure is 1 atmosphere, or 101.3 kilopascals, or 760 millimeters of mercury, the pressure at sea level. That is assumed to be if the weather is okay at those conditions. So then it's easy to compare these volumes of gas to one another. And so standard temperature and pressure is kind of like a reference point that everybody wants to know a particular substance at. Well, at standard temperature and pressure, what is the volume of 1 mole of a gas? Well, at STP, it would always be the same. And so let's go through the mathematics here just really quick. And so at standard temperature and pressure, if we want to know the volume, volume would be equal to nRT divided by P. And the number of moles would be 1 mole. And then R, I chose 8.31 liters times kilopascals per mole Kelvin. And then the temperature is 273 Kelvin because that's our standard temperature. And our standard pressure would be 101.3 kPa because that's what standard pressure is. So if you take these numbers and put them into your calculator and push the button, no matter what units of pressure you use, as long as you match them up with the correct R unit value, you'll end up with 22.4 liters. This 22.4 liters is known as the molar volume of a gas. At standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. Or conversely, 22.4 liters of a gas at standard temperature and pressure is 1 mole. Notice I didn't tell you what kind of gas this was because it doesn't make any difference. It could be a mix of a bunch of gases, but that's the volume that it's going to occupy, and that's why it's called its molar volume, because 1 mole occupies that volume. All right, let's use these ideas, PV equals nRT, these stoichiometry ideas right here to do one sample exercise. We're going to do sample exercise 10.9. It's up here in the textbook. It's on digital book, page 254. I'll write that down here, digital book, page 254. And then let's read the problem. Automobile airbags are inflated by nitrogen gas generated by the rapid decomposition of sodium azide. There's sodium azide right there, and then it decomposes into sodium and nitrogen gas. If an airbag has a volume of 36 liters and to be filled with nitrogen gas at 1.15 atmospheres and 26 degrees Celsius, how many grams of sodium azide must be decomposed? Well, let's go through the steps. The stoichiometry steps right here say first, balanced chemical equation. So balanced chemical equation is given to us. I'm going to write it down here at the top. 2NaN3 arrow 2 Na plus 3N2. And this is a gas right here. That's the gas we're going to end up wanting to know. All right. Or we all know, and we want to find out this mass right here from it. So second, convert to moles. So we're given that we have a volume right here. V equals 36 liters. We're given a pressure of 1.15 atmospheres, and we're given a temperature of 26 degrees C. We've got to add 273 to that to get that to our Kelvin temperature. And then we've got V, P, and T. And if we have V, P, and T, we could find our number of moles right here. So this is a use of PV equals nRT to find our number of moles right here in step 2 of stoichiometry. So N is equal to PV divided by RT. Our pressure is 1.15 atmospheres. Our volume is 36 liters. Our R unit has to be in the pressure units of atmospheres, and the pressure units of atmospheres requires us to have 0.08206 for our units of the R value, 0.08206, and this is in liters times atmospheres per mole times Kelvin. And then the temperature would be 273 plus 26, so 299 I think that adds up to. Let's make sure of that, and then let's put it into the calculator right here. So clearing the calculator, first of all, let's do 273 plus the temperature of 26 to make sure I did that right. And I got 299, that's good. Then let's take our 1.15 multiplied by 36, hit enter. That's the top. Let's divide that by my 299 down here. And then let's take that number and divide it by my 0.08206. And I hit enter. And this is my number of moles of gas. So N is equal to 1.687. We'll carry along a few more decimals right now. So that's the number of moles of nitrogen gas that are needed to fill that airbag. So now we're on to step 3, a mole to mole ratio. So this is my moles of nitrogen gas, and so I'm going to rewrite it over here, 1.687 moles of nitrogen gas, multiply sign, put a line, put nitrogen gas in a position where it's going to cancel, and they want to know the grams of sodium azide right here. So let's put sodium azide as my new set of units right here, and this is moles of it, and this is moles of it. And for every 2 moles of sodium azide, there are 3 moles of nitrogen. If I stopped right there at the end of step 3, I'd have the moles of my sodium azide. But remember, it asked for grams right here. And so I'm going to do my last step, and I'm going to go from moles of sodium azide to grams of sodium azide, which means I'm going to need my periodic table to do that. I'm going to cheat. I'm going to look at the problem right here in the book, and it looks like we have 65 grams in 1 mole of sodium azide. If I take the 1.678 or 1.69 is what they had in the book, times 2 divided by 3, and then I multiply that by 65, I should end up with 73 grams of the sodium azide that's needed. All right, good luck with your gas stoichiometry problems.